hear me well? Or is this better? Okay. Today I'm going to do a coding example workshop again. I got a lot of feedback from you last time that you're interested in image processing and deep learning. So we're going to talk a little bit more about the easy things in deep learning. So if you remember my joke, we're going to talk about the slutty sister of deep learning, which is transfer learning, and she's much easier. What we're going to do today, we're going to look at an application. You don't like my joke? Sorry about it. And we're going to talk about an application in real estate. We're going to try to solve the problem of image classification when you have unsupervised data. So imagine you have all the data from a real estate advertising company like OLX or I don't know, Autodom, and you want to apply some machine learning on the images and extract some knowledge from the images people are posting. And the first natural thing to do is to classify those images. So you can say, you know, this posting had 10 images of the interiors, 5 images of the bathroom, 5 images of the planes, and 5 images of the kitchen. And from that, then you can build more sophisticated models or use that data in some way to analyze conversion, for example. Unfortunately, you don't have pre-labeled data. So you cannot use any pre-trained model to classify your data. It's not going to work. If you use something like the Google model for image recognition, it's probably not going to tell you that this is a kitchen or a bathroom. You need some different approach. And a way to use deep learning quite easily in that is to use transfer learning. And I'm going to give you a short recap of what transfer learning is. You should remember this from my last talk, but let's go into it for a really short while. So transfer learning is when you cut out the last layer from a deep learning neural network. And the last layer usually takes the features that are being extracted by the other layers and then says what's the actual outcome. If you cut away this layer, you get a dense vector of very high level features. So for example, for image processing, you get a vector that in a way says that if there's a face in there, if there's an edge in there, if there is a specific patch of color in there, and you can then feed this data into a different machine learning algorithm. So for example, you can feed this data into support vector machines, or you can put this data into logistic regression, and it's going to work. And in fact, it's going to work much better than applying the same algorithm on the raw data, on the raw image data. So it's a pretty powerful technique that you can use quite easily, because you can download a pre-trained model and use it for feature extraction and then apply it to your own domain-specific problem. So what we're going to do today, we're going to use transfer learning for feature extraction. Then we will cluster these images, and then we will try to find the representative images from these clusters to then classify them and create a supervised model. Okay, so let's start. So first of all, I apologize, but for this data set, I cannot disclose this data set. But I did link a different open data set that you can try at home. So first of all, you can import all the necessary libraries. So this is boring. And then we can see what kind of images we have in our data set. So as you can see, we have different images of houses, and you can see that we have empty rooms, we have the exterior image, we have bathrooms, we have kitchens, the exteriors. So many different types of images of a house. So to use the AlexNet model, this is a Google pre-trained deep neural network model. you can do this. This is commented out because it takes a little bit of time, but you can definitely do it at home with GraphLab. So the only thing you need to do, you need to specify the image column model is auto, and then it uses AlexNet and the output column name, and then you have a dense vector of high-level image features that you can use for other algorithms. And this is a kind of a histogram of those features, and you can see that most of them are close to 0, but there are some ones that are higher. This is a GraphLab canvas visualization, and you can change the bin size if you like to dive a little deeper. So you can see most of them are close to 0, but then there's a lot that are not. And the basic assumption is that if we have two images that are similar, they're going to have a much smaller difference between their vectors. So if you subtract their vectors or take a cosine similarity measure between those the vectors of these images, you will see that for images that are alike, the difference is going to be much smaller. And let's try that here. So we take two images from this data set, and we just subtract them from each other, and we plot the vector. And you see these are two very different images. We have a bathroom here, we have an exterior here. And if we subtract and plot this vector, you see there are big differences. And if we do the same for kind of similar images, two images of a bathroom, you see that this vector is the differences are much smaller. So that in a way visualizes this intuition that similar images are going to have similar vectors. So, is it understandable until now? Yes? Any questions so far? Any questions about the code? Good. Okay, and from that, we can build a similarity graph. So, basically what we're doing here, we are using a nearest neighbors classifier. How many of you know what a nearest neighbor classifier is? Raise your hands if you do. Okay, good. So I will explain for those who don't. A nearest neighbor classifier is basically taking the distance between every pair of examples that you have. And then, when you classify a new example, you try to find from your data set the closest examples, so the one with the smallest distance, and the distance can be a cosine distance or a Euclidean distance or any other distance, and you say, okay, so if my closest example has the label A, so this new example that I don't know what the label is probably labeled A, and the variation of nearest neighbors is k nearest neighbors, which just takes the k nearest examples, so 5 nearest examples, and then it takes a majority vote from them to get the label. So basically we are creating kind of a graph of the closest neighbors for each of these images based on the deep learning features that we have extracted. And if we query it, so if we query it for image 71, so the one that was here, you can see that for this model we get very similar images. So these are images from the data set that were the closest images in terms of the distance of the feature vectors. And what we can do now with this model, we can create a similarity graph, and basically we say create an edge between every image that is in the distance of 0.2 from my image. So this creates a very big graph that's going to be somewhere down there. Okay. This creates a graph of the images that are close to each other. So these images of the bathroom are probably going to be connected with an edge. So we will have a big graph with all the images connected to each other. And what we can do now, so this is just the code, you can code it at home. I don't want to go into explaining every line of code. What you can do now is create a graph out of this similarity graph, and then you can visualize it, and you can see that in our data set, the connections between the images look somewhere like this. So this, in a way, naturally visualizes the clusters that are going to appear and then defines the labels that we might want to assign to the images that we're exploring. So we have about 10 clusters here. So based on that visualization, we can say, okay, I want to cluster these images now. And how many of you know about clustering and k-means algorithm? Clustering, please raise your hand. So most people know, but I will explain it anyway. So clustering is basically, let's say we have 10 buckets, and please put everything that is similar in one bucket, and then everything that is similar to another bucket, and these buckets should be as dissimilar to each other. So we're trying to make groups, logical groups, based on some distance metric from the examples that we have. Is that understandable, or would you like a different way of explaining that? Okay, okay, people do. Okay, good. So basically, what k-means is doing, it's we're saying, give me 10 groups of images, and these images should be in this group most similar to each other. And this is how you can do k-means clustering in GraphLab. And here we say 10 clusters, use this column, and that's it. That's the only thing you have to do. And now we want to, based on the clusters that we have created, we want to assign labels to these clusters. So we want to understand what is inside that cluster and how to best describe it. So we want to assign a human-readable label to the cluster that was an outcome of some abstract algorithm. So one way to do it is just to take a random sample from this cluster and look at these images and make up your mind. Another way would be to take the median of this cluster or the image closest to the median of the cluster and then make up your mind. But there is a better way. How many of you are familiar with PageRank? Okay, so quite a lot for the ones that are not familiar with PageRank. This is the algorithm that was initially used by Google to rank web results. And what it does, it tries to evaluate the strength of a website based on the number of websites that are pointing, hyperlinking to this website. And here we also have a graph, so we're trying to find the most representative image in the whole cluster by evaluating the strength of the links from all other images that are in that cluster. So to do that, we can write a short function. So basically, here we say, give me all images that have this cluster ID assigned. We create a subgraph out of it. We add vertices, which are the images. We add the edges from the vertex that we created before with the k-means algorithm. And we then just run PageRank on it. So this is the only thing you need to do to run PageRank in GraphLab. And based on the PageRank, which assigns some certain weights to each image, we ask this function to output the top, I think, 5 or 10 most representative images of this cluster. And let's see the results. So for cluster 0, these are the results. These are the representatives of cluster 0. Look pretty similar to me. Anyone disagree? Okay. For cluster 2, these are the images there. Pretty similar as well. For cluster 3, the exteriors. Cluster 4, or cluster 8 for some reason. These are the bathrooms. And one thing that is really cool here, these are the bathrooms, and these are the kitchens. And you see that they're pretty similar to each other, but the algorithm was able to actually tell them apart. I think it's mainly because of the stove. Okay, and we also have cluster 9, which are the exteriors without the view of the house. And cluster 1, these are the living rooms. Cluster 4, not so nice bathrooms, so less fancy bathrooms. And a different type of a house. So here you can see that there's a certain feel to these houses. They're a bit taller, they have a kind of a different architecture. And if we go back to the first image of the house, these have a kind of a different feel to it, right? They're smaller, they don't have this weird roof. So you can see that the results that we get from these algorithms are pretty coherent and they're understandable. So what we can do with this now, we can convert our problem to a supervised problem, because now we have labels. So we're gonna do it now. Just let me scroll to that. So these are the labels that we can assign to these images. So kitchens, outdoors, 2 types of bathrooms. These guys decided to join them. Plans, so these were the plans of the house. Empty rooms, living rooms, front house style A, empty rooms with windows, and front house style B. And this is how you can, this is a very simple function that uses that dictionary to convert the label, which is just a number, into the label that is a name. And now we can plot these in a 2-dimensional space, and we can see them on this graph. Just control minus here. You can see them that. For example, empty rooms and empty rooms with windows, pretty close to each other, right? Which is quite intuitive. Kitchens here, also pretty close to bathrooms, and they overlap a little bit in here. We can see that the front of the house, style A and style B, are a bit different. And what else is interesting? And plans are for some reason close to living rooms, which is weird. Okay, that was supposed to be a very short talk, and first time in my life I managed to be on time. So thank you very much. I hope you enjoyed it. Make sure you check out this example. This is actually a working example that you can use with the other data set that I have supplied on our meetup page, and it should work on any computer. The feature extraction is going to be slow, so just put it on, take a coffee, or if you have a GPU, it's going to be fast. But I don't know, I haven't tried. And please try it at home and have fun. Thank you very much.